Space, dark, silent, and infinite. It stretches farther than we can imagine, with distances so great they almost feel meaningless. The nearest star to Earth, Proxima Centauri, lies more than 4 light-years away. Even if you could travel at the speed of light, the absolute cosmic speed limit, it would still take you over 4 years to get there. With our fastest spacecraft, it would take tens of thousands of years. The universe, in its vastness, feels like a prison, not because it has walls, but because of the sheer scale of distance. And yet, there might be a way around this prison, a hidden shortcut through space-time, a tunnel connecting distant regions of the universe. Einstein and his colleague Nathan Rosen proposed it nearly a century ago. They called it an Einstein-Rosen Bridge. Today we know it by another name, the wormhole. What is it? How could it work? And what does it tell us about reality itself? That is the journey we are about to take. To understand wormholes, we must first understand how Einstein changed the way we see the universe. Before him, most people thought of space as nothing more than emptiness, a background stage where planets, stars, and galaxies move around. Time was something separate, an endless ticking of a cosmic clock. But Einstein's theory of relativity shattered that view. He showed that space and time are not separate at all. They are woven together into a single entity, space-time, and space-time isn't just a passive stage. It bends, curves, and stretches depending on matter and energy. Planets bend space-time, and that's what we experience as gravity. The Earth curves space-time, and that curvature holds the moon in orbit. The sun curves space-time, and that curvature keeps the planets circling around it. Space-time is not rigid, it is dynamic. It can bend, and if it can bend, perhaps it can also fold, twist, or connect in ways we are only beginning to imagine. To talk about wormholes, we must first talk about black holes. Imagine a massive star, far larger than our sun, for millions of years. It burns brightly, fusing atoms and releasing energy. But eventually it runs out of fuel. Gravity, which has been trying to crush it all along, finally wins. The star collapses inward. It shrinks smaller and smaller until all of its mass is squeezed into an infinitely dense point, a singularity. Around this singularity, space-time curves so steeply that nothing, not even light, can escape. This is a black hole. To the outside world, the black hole looks like a dark sphere, an event horizon, beyond which no information can escape. To fall into a black hole is to vanish forever from the observable universe. But when Einstein and Rosen studied the mathematics of black holes in 1935, they found something surprising. The equations didn't just describe a singularity, they also hinted at a mirror solution, a possible connection to another region of spacetime. In other words, what we call a black hole could, in theory, be linked to another place. A tunnel, a bridge, a shortcut through the fabric of the universe. The Einstein-Rosen Bridge was born. So what exactly is a wormhole? The best way to imagine it is with a piece of paper. Place 2 dots on opposite ends of the sheet. Normally, to go from one dot to the other, you'd travel across the paper. But if you fold the paper and make the dots touch, suddenly the distance between them collapses. That fold is the wormhole. It doesn't eliminate distance, it reshapes it. It's not faster than light travel in the usual sense. It's a shortcut through higher dimensional geometry. In spacetime terms, a wormhole connects to distant points with a tunnel. Enter one end and you emerge almost instantly at the other, no matter how far apart they may be. It sounds fantastical, but the math of general relativity allows it. The catch is, nature rarely gives us shortcuts for free. The original Einstein-Rosen Bridge, as described in 1935, had a fatal flaw. It was unstable. The moment you tried to pass through it, the throat of the wormhole would collapse. Light itself wouldn't make it across. The bridge would close faster than anything could travel through. So while the equations showed a tunnel, it was a tunnel that pinched shut instantly. A bridge that collapsed before anyone could walk across it. This is why physicists long considered wormholes mathematical curiosities, interesting on paper, but useless in practice. That is, until new ideas emerged. In the 1980s, physicists began asking, what if something could hold a wormhole open? The answer came in the form of exotic matter. Exotic matter isn't alien slime or science fiction fuel. It's a theoretical form of matter with unusual properties, specifically, negative energy density. In our normal world, energy is always positive. You burn fuel, you get heat, light, or motion. But exotic matter would bend spacetime in the opposite direction. Instead of pulling things in like gravity, it would push them apart. If such exotic matter exists, it could counteract the collapse of a wormhole throat, propping it open and allowing travel through. The problem is, exotic matter is not something we can produce in useful amounts. Some effects, like the Casimir effect in quantum physics, suggest negative energy can exist in tiny quantities, but keeping a wormhole open would require far more than we can currently imagine creating. Still, the possibility remains. Here's where things get even stranger. If a wormhole connects to distant points in space, could it also connect to different points in time? According to relativity, the answer is yes. Time and space are linked. If you manipulate one, you affect the other. If you had a wormhole and moved one end near a strong gravitational field, or accelerated it close to the speed of light, time would pass differently for each end. That means you could step into one side of a wormhole and emerge not just far away in space, but also in the past or future. This is why wormholes are often linked to time travel in science fiction, but in physics it creates deep paradoxes. If wormholes allow time loops, could you travel back and prevent your own journey? Could you meet yourself? Could you undo history? The equations allow it. Logic rebels against it. In recent years, a bold new idea has emerged. Physicists Juan Moldacena and Leonard Susskind proposed something known as ER equals EPR. This suggests that Einstein-Rosen bridges ER are connected to Einstein-Podolsky-Rosen entanglement EPR. In other words, wormholes may be the geometric manifestation of quantum entanglement. Entanglement links particles across vast distances instantly. Wormholes may be the space-time equivalent of that link. If this is true, it could mean that wormholes are not just science fiction, they may be woven into the quantum fabric of the universe itself. But have we seen one? So far, no. No telescope has spotted a wormhole. No experiment has confirmed one. And yet scientists are searching. Gravitational wave detectors, like LIGO, might one day pick up the signature of a wormhole collision. Astronomers studying the heart of galaxies wonder if some black holes could hide wormhole throats. And in the future, if quantum computers advance enough, they may allow us to simulate wormhole-like structures on a microscopic scale. The hunt is only beginning. If wormholes can exist, they would revolutionize everything. Interstellar travel would be possible. Galaxies that seem impossibly far could be reached in moments. Civilizations could connect across cosmic distances. Wormholes could even allow us to study the birth of the universe itself, perhaps linking us to regions of space-time beyond the Big Bang. But equally, wormholes could be dangerous. Unstable ones might collapse with catastrophic energy. Traversable ones could create paradoxes we cannot predict. They represent the ultimate gamble, a door to the stars, or a trap of unimaginable consequences. Wormholes are not just about physics, they force us to ask deeper questions. Is the universe fundamentally connected in ways we cannot see? Are space and time really barriers, or just illusions of perspective? If shortcuts through reality exist, what does that mean about the nature of reality itself? Perhaps wormholes are not just tunnels through space. Perhaps they are clues to the deeper structure of existence. Maybe they are telling us that the universe is not a cold, empty void, but a vast, interconnected web, where even the farthest galaxies are closer than they appear. Einstein and Rosen never built a wormhole. They never saw one. They simply followed the equations. And yet, those equations opened a door in human imagination. A door to hidden tunnels through the stars. A door to time itself. For now, wormholes remain theory, but they remind us of something vital. The universe is stranger, more mysterious, and more infinite than our minds can yet grasp. So when you look up at the night sky, remember this. The stars you see may not be as far as they look. The universe may be full of shortcuts, waiting in the darkness, and one day humanity may walk through one. This is not just physics. This is beyond Newton.